Hey everyone, I'm very glad to present our work here. I'm the presenter Wenyu. Our topic is PointCNN-based individual tree detection using LiDAR point clouds. What are the issues? Few scholars have directly applied LiDAR point clouds to 3D neural networks for tree detection, and existing methods usually have better detection results in a specific single scene, but in some complex scenes, the detection results are not satisfactory. Solution. Therefore, we present a PointCNN-based method of 3D tree detection using LiDAR point clouds, which aims to improve the detection accuracy of trees in complex scenes and versatility. There are three kinds of related works. The first one is the raster-based methods. They are susceptible to be disturbed by non-tree objects such as buildings. The second one is the point cloud-based methods. They are not suitable for multiple tree species scenarios. The third one is the method combining the raster and point cloud. They are just with a single tree species. Let me introduce our method. As you can see in this slide, the whole flow chart of tree detection is shown here, with the input of point clouds. This method first builds a canopy height model using raw LiDAR point clouds and obtain rough seed points on CHM. Then it extracts the detection samples consisting of single trees point cloud data based on the rough seed points. Next, the 3D CNN classifier based on PointCNN is adopted to classify detection samples, and the classification results are used for filtering seed points. Finally, our method performs the tree stagger analysis on those close seed points. For building CHM, first, the spike-free algorithm is used to generate the DSM. Then subtract the DTM from the DSM by the LAS tools to obtain CHM. After CHM, we need to generate detection samples. The approach finds those local maxima on the rasterized CHM and regards those maxima as seed points. The approach goes through the following steps. First, a low-pass filter is applied to the rasterized CHM for smoothing the surface and reducing the number of local maxima. Local maxima then are located by using a circular moving window. Last step, the pixel of the CHM is labeled as local maxima if its value is greater than all other values in the window, provided that it is greater than some minimum height above ground. Detection examples are marked as positive examples and negative examples. A positive example consists of a complete tree, and the negative examples are divided into three types, which are incomplete single tree, interlaced multiple trees, single tree intertwined with other things. In this slide, we can see the figure. It is our 3D CNN architecture for classification, based by PointCNN. Then I will introduce our training details. In order to train the 3D CNN classifier fully, 1200 positive examples and 1800 negative examples were manually labeled, 600 for each negative example type. These examples are taken randomly from 6 training props. In this method, dropout is applied before the last fully connected layer to reduce overfitting. We use random optimized with an initial learning rate 0.01 for the training of the model. The classifier filters out non-tree objects, such as buildings, but when the branches of two trees are staggered with each other, it is difficult to detect the trees. So we use tree stagger analysis to solve it. OD represents the degree of stagger between two trees. We set the tree stagger threshold OD equal to 0.1. When OD is lower than 0.1, we regard the two seed points as two trees. When OD is equal or higher than 0.1, we regard the two seed points from the same tree, and seed point with a smaller radius is deleted. The calculation process is shown as follows. Let me show our detection results. This table shows that our method can extract trees well. This slide shows the process of seed point filtering. This slide shows detection results on point cloud data in 6 plots. This slide shows detection results on CHM in 6 plots. This slide shows comparison with related researches. Our method has the best matching score. It means our method has better tree detection results in complex scenes. Conclusion. The experimental results show that the proposed method has lower commission and omission when detecting trees, and has better versatility for complex tree scenes. Something about future work. Tree detection in tall dense forest remains an open challenge because of increasing occlusion levels towards the ground. Although our method improves the detection accuracy in multi-tree species scenes, our method may fail to detect the understory trees due to the occlusion of the overstory trees. when there are a large number of understory trees in high dense forest. In the future work, we will solve the problem of occlusion by overstory trees. That's all. Thank you for your attention.